Let's dive into the fascinating world of feed-forward propagation and backpropagation in artificial neural networks. These two processes are crucial to training a neural network efficiently. So let's break it down step by step. First up, feed-forward propagation. This is where data travels through the network, layer by layer, from input all the way to output. Imagine it like a line of kids passing a ball down the line, each one getting the ball, doing something with it, and then passing it on. So during this process, each neuron in a layer takes inputs, applies weights and biases, and then with an activation function, it decides whether to pass the information forward. Sounds simple, right? Well, it gets a bit more intricate, as we'll soon see. Now let's talk about backpropagation. This is like a guide helping the network learn from its mistakes. When the network makes a prediction, it checks how far off it was from the actual result, like a teacher giving feedback on a test. The error travels back through the network, adjusting those weights and biases to improve the model for the next time. It's a vital feedback loop that keeps on fine-tuning the network's performance. Now, as we explore these mechanisms further, I'll also provide some code examples to illustrate these concepts in action. You'll see how straightforward it can be to implement these ideas in programming. So stay tuned, because we're just getting started. So far, we've explored artificial neural networks, or ANNs, as a supervised learning algorithm that mimics brain function through their architecture, which consists of interconnected layers of neurons. We've also discussed the training process using backpropagation and even implemented a simple digit recognition ANN with Python and TensorFlow, making good use of the MNIST dataset. Then we took it a step further by transitioning from a basic ANN to a convolutional neural network, or CNN, to really enhance image classification. Finally, we touched on various techniques to boost model performance, highlighting the importance of experimentation in neural network development. Now, we're diving into the intricacies of how data flows through neurons by means of feed-forward propagation, and how our network learns through backpropagation. Let's break it down. When we talk about feed-forward propagation, we're referring to the way input data moves through the network from the input layer through the various hidden layers and finally to the output layer. At each neuron, the input is multiplied by weights, summed up, and passed through an activation function, which decides whether the neuron should fire. It's like the network is making decisions at every layer based on what it learned during training. And that brings us to backpropagation, which is where the magic really happens. After a forward pass is completed, the network compares the output to the expected result and calculates the error. This error then travels back through the network, adjusting the weights of the neurons to minimize that error. Essentially, it's the network learning from its mistakes. So, through these two processes, feed-forward and backpropagation, our neural network is constantly evolving, improving its ability to predict and classify data. Pretty cool, right? Let's keep unraveling this fascinating journey through neural networks. The process of feed-forward propagation, let's dive right in, begins when we input data into the neural network. Picture this. Each layer of neurons, it's like they're processing data and then passing it along to the next layer, just like sending something through a series of doors. Each door, or neuron, it applies a specific question. Think of it as an activation function to decide whether to open and let the data through. Now, mathematically speaking, when data travels from one layer to the next, we apply a linear transformation first, followed by a nonlinear activation function. For example, using the popular ReLU, which stands for rectified linear unit, it introduces that important nonlinearity that we need to model more complex relationships. So, by leveraging these layers and functions, we can really get into the intricacies of how neural networks work. Now, let's take a look at how we can implement a simple feed-forward propagation using a single-layer perceptron. We start by importing NumPy, which is essential for mathematical operations in Python. First, we're going to define the rectified linear unit, or ReLU, activation function, which will help us introduce nonlinearity to our model. The next step involves setting up our weights and biases. Here, we've chosen specific values for the weights as a two-dimensional NumPy array and initialized the bias as a one-dimensional array. With our input data prepared, we then define the feed-forward function, which computes the output of the neuron. This function performs a linear transformation by calculating the dot product between the input data and the weights, followed by adding the bias. After obtaining this combined value, we apply the ReLU activation function to determine the final output. Finally, we test our implementation by running the feed-forward function with submitted input and printing the output. This straightforward code structure effectively illustrates the core principles of how data flows through a single-layer perceptron and feed-forward propagation. In this code, we're going to define the ReLU function, which is essential for calculating the output of each neuron. To start, we initialize a random set of weights and biases. Next, we define our input data. Now, the magic happens in the feed-forward function, which computes the network's output. It does this by performing a linear transformation. Think of it as taking the dot product of our input data and these weights, and then we add the bias. Finally, we apply the ReLU activation function. It's a smooth and effective way to introduce nonlinearity into our model, allowing it to learn from the data. So let's move forward with coding this up. Now that we understand how feed-forward propagation works, let's shift our focus to backpropagation. Backpropagation is really the heart of neural network training. Its main purpose is to minimize the loss function, which quantifies how far off our predictions are from the actual labels. You can think of it as a feedback loop. After making a prediction, we need to know how to adjust our weights to improve future predictions. So during backpropagation, we calculate the gradient of the loss function with respect to each weight by applying the chain rule of calculus. This is essential because it helps us understand both the direction and the magnitude of the weight updates we need to reduce our prediction error. All right, let me walk you through a simple example of this process. You'll see how exciting it is. Now, let's dive into a straightforward example of backpropagation, following our exploration of feed-forward propagation. The target variable, if you recall, represents our expected output, or true labels, super important for figuring out how much our predictions deviate from reality. Next, we're going to define a simple loss function. In our case, that's the mean squared error between the model's output and the target. This function helps us quantify how well the model is performing. When we compute the loss with this function, it shows us how well the model predicts those target values, and basically a lower loss is a sign of better performance. Now, on to backpropagation. In this process, we first compute the error by subtracting the target from the output. This gives us a peek into our prediction accuracy. Then we calculate the derivative of the loss, keeping in mind the properties of the activation function we used in our model. After that, we compute the gradients necessary to adjust our weights, using both our input data and the error from the model's output. Finally, we update those weights based on the gradients we just computed and a defined learning rate. This step is crucial because it ensures our model learns and improves its predictions with each iteration. This entire cycle, my friends, allows our neural network to refine its weight adjustments, ultimately boosting its predictive capabilities. Here, we're going to define a simple loss function to measure the error between the model's predictions and the actual labels. In the backpropagation function, we'll compute the derivative of the loss with respect to the output. This step helps us determine how to adjust the weights that our model is using. Now, once we've got those adjustments figured out, we update the weights according to a learning rate. The learning rate is crucial because it controls how much we change those weights during each update. It's like setting the pace for learning, ensuring our model improves without overcorrecting. So to recap, we define our loss function, calculate the derivative, and then adjust the weights based on that learning rate. Simple, but effective.
At this stage, our neural network is equipped to learn from its mistakes.
However, real-world training can get a bit messy, especially when we dive into multi-layered networks. So let's explore the ins and outs of backpropagation in a multi-layer neural network. In a more complex architecture with those extra layers, the process remains fundamentally similar, but there are a few additional steps we need to consider. Each layer's weights must be adjusted based on the gradient calculated for that specific layer. This means we need to. At this stage, our neural network is equipped to learn from its mistakes. However, real-world training can get a bit messy, especially when we dive into multi-layered networks. So let's explore the ins and outs of backpropagation in a multi-layer neural network. In a more complex architecture with those extra layers, the process remains fundamentally similar, but there are a few additional steps we need to consider. Each layer's weights must be adjusted based on the gradient calculated for that specific layer. This means we need to propagate the error backwards through each layer of the network. Let's break this down with an example. A neural network featuring an extra hidden layer. First things first, we have to tweak the feed-forward step to account for this hidden layer. So imagine this. You're passing information from the input layer through to the hidden layer, making calculations along the way, and ultimately reaching the output layer. As we calculate the output, we also need to keep track of how the weights in each layer relate to the error that we observe. Whoa! This means recalculating gradients at each layer, working back from the output, adjusting the weights, and ensuring the model learns effectively. Isn't that fascinating? So now let's put this into practice and visualize how these intricate adjustments come together.
Now, let's take a look at how we can implement feed-forward propagation in a multi-layer neural network. In this code snippet, we begin by defining the weights for two separate layers, the weights from the input layer to the hidden layer and from the hidden layer to the output layer. Here, we initialize these weights using random values, establishing the essential parameters that will determine how our input data flows through the model. Next, we define a function called feed-forward multilayer, which takes the input data along with our weights for both layers. Inside this function, we first compute the activation of the hidden layer by performing a dot product of the input data and the weights leading to the hidden layer, followed by applying the ReLU activation function to introduce the necessary nonlinearity. This output is then passed as input to the next layer, where we again apply the dot product with the output layer weights and the ReLU function to compute the final output. Finally, the function returns both the hidden layer's output and the final output, allowing us to inspect the flow of data through the network and see how the model transforms the input into various representations across layers. This structured approach not only highlights the computations made within the network, but also emphasizes the importance of layer-wise transformations in the learning process.
In this snippet, we're diving into the world of neural networks, specifically focusing on how we set up the weights for two layers, from the input layer to the hidden layer, and from the hidden layer to the output layer. Now, we'll adjust our feed-forward function, not only to compute the output for that final layer, but also to take into account the hidden layer. This is crucial because it allows us to really understand how data moves through multiple neuron layers, capturing the intricacies of data flow. So, as we make these adjustments, think about how each layer interacts. It's like building a bridge, where every component has to work together to ensure smooth passage. Let's visualize this process as we go along, and I'll guide you through each step to make sure everything connects. Next, we need to implement backpropagation for this multi-layer structure. So, backpropagation basically involves calculating gradients, right? We do this layer by layer, moving backwards from the output layer to the input layer. Now, it's important to note that the weight updates for the hidden layers and the output layers are going to differ, because each layer has its own gradients to work with. So keep that in mind as we tackle this, yeah?
Now, let's take a moment to dive into the backpropagation process for a multi-layer neural network. The backpropagate multi-layer function is built to adjust the weights for both the hidden and output layers, and it does this based on calculated errors. First off, we calculate the error at the output layer by subtracting the target values from what our model predicted. Then we apply a derivative calculation, which uses the unique properties of the activation function to figure out how to adjust those weights.
Next up, we compute the gradient for the weights that connect the hidden layer to the output. This is key, as it allows us to update these weights using a defined learning rate, making sure they align better with our predictions. Now, the process moves backward as we start propagating that error back to the hidden layer. By applying the derivative of the activation function again, we can calculate how much each weight in that hidden layer should be adjusted. It's like fine-tuning a musical instrument. Finally, we update those hidden layer weights in a similar fashion. This iterative adjustment process is super crucial for minimizing prediction errors, as it ensures our network becomes better at making accurate predictions over time. After that, the updated weights are printed out, which illustrates the learned modifications after just one step of backpropagation, a fundamental aspect in the training of neural networks. In the backpropagation function for our multilayer network, we start by computing the error and gradients for the output layer. Now, don't worry if that sounds a bit technical. Let's break it down. Once we have those computed, we apply the same process to the hidden layer. This is crucial because it allows the network to learn from its mistakes, Next, we update the weights for both the hidden and output layers accordingly. This updating step is what helps our network refine its predictions, improving over time as it learns from the data it processes. So, step by step, we're guiding our model closer to accuracy. And that's essentially how we enhance our network's performance through backpropagation. So, why do we keep repeating feed-forward and backpropagation during training? It's all about gradually improving our model's accuracy through many iterations. Each cycle adjusts the weights based on the latest prediction errors, pushing the loss down towards zero. This repetitive process, it's often encapsulated in what we call an epoch. In practice, we set the training to run over several epochs, allowing the model to learn incrementally. It's like a gradual refinement, where each round builds on the last, steadily optimizing the model. When training your neural network, it's really important to keep an eye on your loss after each epoch to make sure your model is actually learning. Now, if you notice the loss plateaus, this might be a sign to adjust your learning rate, or maybe even increase the number of layers, or try out some different activation functions. As you work through this process, you'll begin to develop a keen eye for the right hyperparameters that help your model converge to something more accurate. So keep experimenting and pay close attention to those loss values. It's all part of the journey to building a better model.
The plotted figure displays loss value over epochs during training, with epochs on the x-axis from 1 to 100 and loss values on the y-axis. Now, let's take a closer look at the main pattern here. It shows a clear exponential-like decay of loss as the training progresses. We start with a relatively higher loss value in the early epochs, and it drops sharply during that initial phase. You'll notice that steep slope in the first tens of epochs. After that, it transitions into a slower decline and approaches a low asymptotic value as we move to the later epochs. Each epoch is marked with a green circular marker connected by a green line labeled loss value. These markers reveal small random fluctuations around the overall downward trend, which indicates some noise or variability at each epoch. This aligns with a small Gaussian perturbation. Now, the grid and axis tick spacing make it clear that most of the meaningful decrease happens before roughly epoch 30. From around epoch 30 to 100, you can see the curve flattens, suggesting diminishing returns for further epochs. So, what can we conclude from this visualization? Well, it implies that the training process is converging effectively. The rapid early reduction signals effective initial learning. This suggests a suitable learning rate and model capacity, while that later plateau indicates the model is getting closer to an approximation of the minimum loss given the current hyperparameters. Those small oscillations around the trend hint at low-level stochastic updates. Keep in mind, the noise magnitude is relatively small compared to the overall drop. So if you're looking for faster convergence or a lower final loss, you might want to focus your tuning efforts on those earlier epochs, like adjusting the learning rate schedule, incorporating more data, or applying stronger regularization. Importantly, though, this figure shows only the training loss. It confirms the internal convergence behavior, but doesn't speak to generalization without a separate validation curve.
The excitement of neural networks lies in experimentation and discovery. Whether you're implementing advanced optimizations like momentum or the autumn optimizer, or using techniques such as dropout and batch normalization to prevent overfitting, there's always something new to learn and discover. It's like every time you dive deeper, you uncover a new tool or tweak that can enhance your model. So, for instance, when you're playing around with the autumn optimizer, you might notice how it adjusts the learning rate dynamically, adopting as it goes. That alone can lead to some significant improvements in performance. And don't get me started on dropout. It's such a game changer for regularization. It helps you avoid that pesky overfitting by randomly dropping units during training. Batch normalization is another fascinating technique. It allows for faster training and can even provide some regularization benefits, which means you're less likely to see your model getting stuck in local minima. So the more you explore these components, the more tools you have at your disposal to tackle complex problems. Isn't that just incredible?
Now that you've got a grip on feed-forward and backpropagation, you're well on your way to developing robust neural networks. But the journey doesn't end here. As you advance, you'll uncover even more sophisticated methods and practices, things that can really take your models to the next level. And hey, never underestimate the power of community and resources in this field. Online platforms, forums, and open source libraries, they can provide unparalleled insights and tools that will aid your learning and projects. And above all, remember that persistence is key. Neural networks can be intricate, but with practice, you can harness their potential to create transformative applications. So keep pushing forward.
In summary, mastering feed-forward propagation and backpropagation is a significant milestone in your machine learning journey. You now possess the fundamental tools to build and train effective neural networks from scratch. Keep experimenting and keep learning. Because as always, it's about pushing the limits of what artificial intelligence can achieve. So, dive in, get your hands dirty, and let's see where your creativity takes you next.